This is lesson 4.7, coordinates and change of basis. So in this lesson, we're going to do exactly that. We're going to start with this idea of coordinates. We'll define that and look at what exactly that means. And then from that, we'll launch into this whole idea of change of basis. A lot of new material in this, but certainly some ties back to things we've done in the past. So let's go ahead and take a look at what it means as far as coordinates go. So we've got coordinates relative to a basis. It says let B be the set V1 to Vn be an ordered basis for a vector space V, and let X be a vector such that X is basically a linear combination of those vectors in B. The scalars C1 to Cn are the coordinates of X relative to the basis B. And the coordinate matrix or coordinate vector of X relative to B is the column matrix in Rn whose components are the coordinates of X. All right, what did we just read? What in the world is this? Okay, let's break this down. So B is simply a basis for a vector space V. Remember again, basis just means that the vectors in B, the linear combinations of the vectors in B, will give us all of the vectors in the vector space of V. So B is a basis, linear combinations create vector space V. X is just an arbitrary vector in V. So X is one of those linear combinations created out of B that we would find in V. Okay? So that's all should be old stuff that we've learned and know already. Then it says the scalars, and this is where we get into the new now. So it says the scalars in that linear combination are the coordinates of X relative to the basis B. So in other words, we're going to start calling these scalars now in this lesson. We're going to start calling these scalars coordinates of X. You'll notice up in the first sentence, it talked about an ordered basis. We've never talked about ordered before. We've always just called it a basis. The idea behind this idea of ordered basis simply means now that the order of the vectors is actually important in the sense that we want to make sure that the coordinates, these scalars, are matching up in the corresponding order of the vectors. So the idea that if I'm going to say that C1 times V1 and C2 times V2, that those combinations, those multiplications are important, I want to make sure then that when I'm talking about the scalars, that C1 and C2 come in the same order as V1, V2. Okay, so just a slightly new idea there with the ordered, but basically what we're saying now is that the scalars are coordinates of X relative to the basis of B. They're the coordinates or the scalars that we're using in basis B to come up with all of those vectors. Okay. The coordinate matrix of X relative to B is the column matrix in R whose components are the coordinates of X. In other words, all we're saying is that the coordinates of X, the coordinate matrix, that's what this symbology means. So coordinate matrix of X relative to B, that's how we're going to write that symbolically. And that is simply a one-column matrix of all of our scalars. All right. So let's kind of put this into an example and see what this is exactly all about. So example 1 says, find the coordinate matrix of X equal 5, negative 3 in R2 relative to the standard basis X, S equals 1, 0, 0, 1. This is about as basic an example as we can get, and then we'll do one that's just a little bit more to it. But the idea here is that if X is 5, negative 3, I want to create a linear combination from S that is going to give me that vector 5, negative 3. So very simply, if my first vector is 1, 0 in S, and I need to get a 5 out of that, I'm going to multiply that by 5. And then plus, if my second vector is 0, 1, and I need to get a negative 3 out of that, I'm going to multiply that by negative 3. So in other words, we use the vectors in S, and these are my scalars, 5, negative 3. So because those are my scalars, or my coordinates, we're going to say that the matrix of X relative to the basis S is simply going to be a one column matrix with those scalars 5, negative 3. So in this case, the vector x, the elements in x, happen to be the same values as they are in our matrix, in our coordinate matrix. Okay, that will only happen when you're using the standard basis like this. Okay, but that's the idea is we're taking this, this arbitrary vector in V. We've got a basis S, right? So that's what's going to give us all of the vectors in V. And we simply want to know what is the coordinate, the coordinate matrix of X relative to, in this case, S. We're calling it S instead of B. And in this case, it's 5, -3, because those are the scalars that I would multiply 1, 0, and 0, 1 by to get X. Okay? So let's do another example, one that just has a little bit more to it. So here it says the coordinate matrix of X in R2 relative to the non-standard ordered basis. So non-standard just means it's not going to be the 1, 0, 0, 1. So here we've got non-standard ordered basis B given by 2, -1, and 3, 1. And this time they're telling us what the coordinate matrix is. The coordinate matrix is 4, -3. And what it asks us to find is the coordinate matrix relative to the standard basis B prime, which is the 1, 0, 0, 1. Okay, so a little bit different here too, because what we're going to do now is we need to figure out what is the vector being created by B, right? By this set and by the coordinate matrix. So we're going to figure out that vector first, and then we're going to use really that vector to find this coordinate matrix in terms of or relative to the standard basis. So here's how this looks. We know that X is going to be basically 4 times 2, -1, right? Because our first scalar is 4. We're going to multiply that by the first vector in B. And then plus, now my second scalar is -3. And we're multiplying that by the second vector, 3, 1. Again, that idea of ordered basis, that's important. So that's going to give me, if I just simplify this down, 8 minus 9 is a -1, and -4 minus 3 is a -7. Okay, so that is the vector that we get through the linear combination created by that information above. So that now is what we're going to use to find this coordinate matrix relative to the standard basis B prime, which is 1, 0, 0, 1. So just like we did before, -1, -7 would be -1 times 1, 0, plus -7 times 0, 1. And therefore, because the scalars are -1 and -7, the coordinate matrix of X relative not to B, but to B prime, right? Because that's this, right? B prime is -1, -7. All right, let's do one more and see if we can kind of put this together now in a final example, and then we'll move on then to some other ideas here. So find the coordinate matrix of X equals 9, -4, 17 in R3 relative to the non-standard basis. Okay, so this is definitely a little bit different now, because now we don't have nearly as much information as we've had before. Before we've had the coordinate matrix, we've had other information. This is going to take us into some stuff that we've done many times before. It's going to look similar to processes we've done before. Here's the idea. So we know that X, right, this 9, -4, 17, that's a vector in V, or in this case specifically in the 3 space of R, that is produced by a linear combination of the vectors in B prime. So in other words, I know that if I take C1 times U1, not V, we're using U here, plus C2 times U2, plus C3 times U3, that is going to give me that vector 9, -4, 17. So in other words, X, which is 9, -4, 17, is equal to some scalar c, we don't know what the scalars are in this one, times the vector 1, negative 2, 3, plus some scalar c2 times the vector negative 1, 3, 0, and then plus some scalar c3 times the vector 2, negative 5, and 5. And what we need to do is we need to find C1, C2, and C3. So we're going to do this how we've done this so many times before. We're going to set up a system of equations. We know that C1 times 1 plus C2 times negative 1, which is a negative C2, plus C3 times 2 has to equal the first entry of 9. And then continuing, we've got negative 2C1 plus 3C2 minus 5C3 is equal to negative 4. And then finally 3C1, no C2 in this case, and then plus 5C3 is equal to 17. Okay. So basically then the idea is if I took normally you do an augmented matrix and that's what we're going to do kind of on the side. But the idea here is if I take that coefficient matrix, 1, negative 1, 2, negative 2, 3, negative 5, and 3, 0, 5, if I multiply that by C1, C2, C3, that's going to give me 9, negative 4, 17. Okay? And so again, the idea is we're trying to solve for that one column matrix of scalars. We're trying to find the coordinates. So I'm not going to write this all out, but obviously we just we'd create the augmented matrix. We'd apply Gauss-Jordan elimination. And what we'd find is that C1 is 49, C2 is negative 12, and C3 is negative 26. Okay? So in other words, X is 49 times 1, negative 2, 3, plus a negative 12 times negative 1, 3, 0, and then plus a negative 26 times 2, negative 5, 5. So our coordinate matrix then, relative to B prime, is simply that one column matrix, 49, negative 12, negative 26. All right. Hopefully that part of the lesson makes sense. We're gonna kind of build on this now. So if it's not making sense, I would encourage you to maybe go back and maybe relook at some of the examples and just make a little more sense of that before you move on. But when you're ready, let's go ahead then and talk about kind of the other half of this lesson in terms of what we're dealing with, and that is this idea of change of basis. So it says, given the coordinates of a vector relative to basis B, change of basis is simply the process of finding the coordinates relative to another basis B prime. Okay. It's not that much different from what we've already been doing. We're just going to add a little bit more detail to it. So from example 3, B is the standard basis. Then finding the coordinate matrix of X, the one that we just did, right, 9, negative 4, 17, relative to the basis B prime, is simply a matter of solving for C1, C2, C3. That's what we did, right? So we set up this equation, right? That's why I kind of wrote it like this to make this connection. So we had this equation, all right, and we basically used that, obviously in augmented matrix form, but we used this to solve for C1, C2, C3. What I want to do is kind of relabel some of these things now and talk about these in new definitions, in new terms. So I'm going to call this first matrix, which we normally think of as our coefficient matrix, I'm just going to call this P. The C1, C2, C3, we already know, right? When we solve for C1, C2, C3, we put that into this matrix down here, and we called that the coordinate matrix relative to B prime, and that's exactly what it is. So I'm going to call it exactly that. This the coordinate matrix of x relative to b prime. And the 9, negative 4, 17 is the matrix of x relative to b, relative to the standard basis. All right? And so let me write that out. P is what we are going to call the transition matrix from B prime to B. From B prime to B. In other words, when I take the coordinate matrix of x relative to B prime, when I take those scalars and I multiply it by the transition matrix, it will give me the coordinate matrix of x relative to B. So B prime to B, B prime to B. And then just to clarify, just so you've got it here right with this. So again, the other two parts, the second part is again the coordinate matrix. This goes back to our earlier definition. So the coordinate matrix of x relative to B prime, relative to B prime. And then we've got the coordinate matrix of x relative to B. So the coordinate matrix of x, coordinate matrix of x relative to B. Okay. So what we're going to do now is we're going to use this idea and this information. We're going to start to find coordinate matrices now, and we're going to start to find these transition matrices. All right. So let's go ahead and jump to an example here. I'm sorry, theorem first and then example. So this theorem is kind of tying what we just talked about to the actual process that we're going to use to do this. So this says that B and B prime are two bases in the n space of R. Okay, so B we're going to represent by V vectors, and B prime we'll use U for the vectors. It says the transition matrix P inverse from B to B prime can be found using Gauss-Jordan elimination on an n by 2n matrix where we're going to adjoin B prime and B. Okay, now let me just pause for a minute. Let's go back up here for a minute. Because here, we said that P, right, so all of a sudden they introduced this P inverse. Where did that come from? Well, we said that P, right, P is the transition matrix from B prime to B, all right? In other words, P, think of it like a function, right, where it's taking us from B prime to B. It's mapping B prime to B. Well, here now, the inverse function, if you think about what an inverse function does, right, it undoes what the function was doing. So squaring the inverse function, square roots. Multiplying the inverse function, divides. Here, the function P, if you want to think of it as a function, is a transition matrix from B prime to B. Here, the inverse is from B to B prime. So that's all we're doing is we're reversing this, and we're going to use P inverse to take us from B to B prime. All right. And how do we do that? Well, again, we're going to set up this adjoint matrix where we're going to take B prime and B, create one matrix out of that, use Gauss-Jordan elimination, right? That's using the Gauss-Jordan elimination to get an identity matrix, and whatever's left is going to be our transition matrix, our P inverse. So how does this look exactly? Find the transition matrix from B to B prime. So again, B to B prime, we're looking for this P inverse. For the bases for R3 below. So we've got B is a standard basis, and then we've got B prime, which is another basis. And so again, to find the transition matrix, what we are going to do is, again, create that adjoint matrix, and we're going to use that to find P inverse. So I'm going to write this as 1. Oh, and I should mention, by the way, when we're doing this, that we want to think of, we write B prime, we don't want to write 1, 3, 3, 1, 4, 3 as row vectors. We want to think of these as column vectors. So I'm actually going to write this 1, 3, 3. You know what? I'm gonna. Sorry about this. We're punting here. I'm gonna change these values because I wanna make a connection back to what we did earlier. So I'm gonna change these values, and I want to change these values to what we were doing earlier in example 3. So I'm just gonna do this. Apologize for this, but let me just copy this, and let's just do this. Let me just. All right, there we go. So we're gonna use this instead because, again, I wanna kind of make the connection to what we did earlier with this example here. So I'm going to, again, we're gonna start by making that adjoint matrix. So again, 1, -2, 3. I'm gonna write that in column form. -1, 3, 0, and 2, -5, 5. The reason that I'm doing that is actually for that reason that we did back in example 3. In example 3, right, we set up the system, and when we set up a system, these first terms, right, created the first row. The second terms created the second row, and so on. So that's really all we're doing is we're just putting this in that same form, okay? And let me do this in blue just so it doesn't get lost in this. All right, so now again, so that's B prime, right? That's B prime, but I also want to put B next to it, and B is the standard matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. Obviously, row, column, it doesn't matter with that one because it's the same thing either way. So again, if I apply now Gauss-Jordan to this, what I'm going to get is obviously now on the left side, we're going to have the identity matrix. On the right side, we're going to get this P inverse, this inverse P matrix. And that matrix is 7.5, 2.5, and -0.5, -2.5, -0.5, and 0.5. And then -4.5, -1.5, and 0.5. And I would certainly encourage you to actually plug that left-hand matrix into your calculators or use an online tool and just run a row-reduced echelon form and see that it does create this matrix. So bottom line is, again, we started with B, not inverse, B prime and B. And what we end up with is the identity matrix and P inverse. So what that means then is that our transition matrix is, and I'm going to cheat here a little bit, and I'm going to copy this, so I don't have to rewrite all of that. But that is our transition matrix that we needed to find, okay? So let me kind of make a stronger connection back to 3. I mentioned that, we write B prime. When we wrote this matrix, we wrote it because it's basically writing out the coefficient matrix for the system of equations. But also the other thing that happens is, remember from example 3, so from example 3, we said that x was 9, -4, 17, okay? If I take P inverse and I multiply it by the transpose of x, obviously I can't multiply it by x as it is. It doesn't work. So I'd have to transpose it so I've got the right number of columns and rows. But if I do that, what I get is I get a column matrix 49, -12, -26. And those numbers should look familiar because basically what I'm saying then is that when I take the transition matrix and multiply it by x, I get this column matrix. Well, if I go back to number 3, there's that column matrix, okay, relative to B prime. We basically took B and transitioned it to B prime using this transition matrix that we found. All right, let's move on. Just a few more examples. We're going to do 3 more examples. We're going to do this one. And then the last 2, really not much of examples at all. It's just to show that we don't have to always be in the n space of R, that we can do this for other vector spaces. But this is kind of our last big one, and that is, again, just find the transition matrix from B to B prime for the bases for R2 below. So notice now, I just wanted to do one where we didn't have a standard basis, but it's the same process, okay? So again, I'm going to start with B prime on the left side and making sure again that we do kind of think of those as columns. We're going to write it like this, and then write B, same thing. I'm going to write those as columns. So -3, 2, and 4, -2. So this is B prime, this is B. And again, using Gauss-Jordan elimination to simplify this down, we get 1, 0, 0, 1. We want that identity matrix, right? This is the identity matrix in the 2 space. And then we get -1, 2, -2, 3. And that's our inverse, or excuse me, our transition matrix. So P inverse is the matrix -1, 2, -2, 3. So this is the transition matrix from B to B prime. Okay. Now, what if you forgot, you messed up, and you accidentally switched B and B prime? Because it's pretty easy when you're setting up this first matrix to forget that you actually have to flip it. You don't want B, B prime, you want the B prime first. So let's say I accidentally flipped this around and I wrote -3, 4, 2, -2, -1, 2, and 2, -2. And I go through and I apply Gauss-Jordan and I get my 1, 0, 0, 1. What I'm going to end up with is obviously I'm not going to get P inverse. I'm not going to get -1, 2, -2, 3. What I do end up with, though, is 3, -2, 2, -1. Basically, all I've done is if you pay close attention to this and to this, they are inverses of each other. That's all they are. The determinant of these matrices is 1. And if you remember how to find an inverse, you take 1 over the determinant, and then you flip in a 2 by 2, you flip the one diagonal, and you change the signs in the other diagonal. So here, the determinant is 1, so that's not going to change any of the values. If I flip the -1 and the 3, the -1 and the 3 flip, -2 on the bottom becomes +2. The 2 on the top becomes a -2. They're inverses of each other. And what that tells me also then is that this is P. So this is P inverse, this is P. If I were to multiply these together, I get the identity matrix. So this then is actually not the transition matrix from B to B prime, but it's the transition matrix from B prime to B. Okay, one undoes the other. So one takes it B to B prime, the other takes it B prime to B. All right, so that's how you find a transition matrix, is you just use that process, create that adjoint matrix, apply Gauss-Jordan, and you've got your transition matrix. All right, well, as I mentioned earlier, we're going to finish up with 2 last examples here that just simply show how we can use this in other spaces beyond just the R space. So in this case, we're going to look at polynomials. We're going to look at the P space. So it says find the coordinate matrix of P equals -2 minus 3x plus 4x cubed relative to the standard basis for P3 given by S equals 1x, x squared, and x cubed. Okay, so again, we're not really doing a whole lot of work here. We just want to put this, we want to find the coordinate matrix. We want to find that 1 column matrix of scalars. All right, so if I think of this as, again, in order to take P and using the standard basis here, the first term -2 would be multiplied by 1. And then I'd have plus a negative 3 times x, and then plus 0 times x squared, and then plus 4 times x cubed. In other words, these are the scalars that I would multiply by the elements in the standard basis to get p. And therefore, my coordinate matrix of p relative to basis s is simply negative 2, 3, 0, 4. It's a lot like that very, very first example we did to start off this whole lesson, okay? So in other words, the coordinate, I can say that the coordinates matrix, so coordinate matrix of a vector in P3 is very much the same as what we would write for a vector in R4. So we can say that coordinate matrix of a vector in P3 is a vector in R4. Okay. All right, let's do our last example here. And now we're going to do one with matrices. So find the coordinate matrix of x equals 2, negative 1, 4 relative to the standard basis for M31 given by, again, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so here, again, if I want to take this, this vector, which is in matrix form 2, negative 1, 4, and write it as a linear combination of the vectors in S, I would take 2 times 1, 0, 0 plus negative 1 times 0, 1, 0 plus 4 times 0, 0, 1. So again, here are my scalars. That's going to create my coordinate matrix. So my coordinate matrix of x relative to S is the column matrix 2, negative 1, 4. And in this case, then, I can say that a coordinate matrix, so coordinate matrix in M31 is a vector in R3. So bottom line is that basically what we're saying then is you can represent vectors in any n-dimensional space. So whether we are using matrices or polynomials or straight up vectors, regardless of the vector space that you are in, we're able to represent those vectors using the same notation that we use in Rn. Okay? So as you know, regardless of the type of situations that you find yourself in, your solutions are always going to be, those coordinate matrices are always going to be represented by something similar to Rn. All right, so we've got coordinate vectors, we've got change of basis, or I should say coordinate matrices and change of basis. A lot packed into this. Again, go back and watch some of those examples if you need to see that. Book has other examples as well that you can look at. As always, please reach out if you have any questions or just need clarification on anything. I'm happy to help out. Otherwise, I will see you in the next lesson.